Hello folks, today in this video, I'd like to talk about wave properties. We're going to take a look at like the properties of waves and what kind of different things they can do, as well as analyzing the speed of a wave and the actual particulars of a wave's motion. Let's go ahead and get started. So when you think about what a wave is, you often probably will think about things you've seen in your life, ocean waves or the wave at a stadium when people are doing the wave. And I want to think about like what are some of the things that make a wave a wave. So the first thing I think about is that a wave pulses. A wave moves up and down if you're moving a slinky through, right? A wave pulse is one repetition or a cycle of a wave. And then what makes a wave is that wave repeats. So you get a periodic wave when multiple wave pulses repeat in a regular pattern. So like this one here where the person's moving the slinky up and down and up and down, that's what really makes a wave, that periodic motion. I'm using that word because you might recall our very first module here was talking about periodic motion or simple harmonic motion. So I want to do a quick recap about some concepts from periodic motion. The first one is that we can describe the position of a particle in a periodic motion or in a wave using this function, where that position is the amplitude of that wave times this cosine function, where it depends on the angular frequency, the time, and the phase angle. You might also recall some definitions like period and frequency, where period is how long it takes for one wave cycle to occur, whereas frequency is the number of cycles you have in a particular or in a second. And those are related as inverses. The period is the inverse of the frequency and vice versa. Lastly, we learned about omega, which appears up in this equation too. Omega is the angular frequency, which you can calculate using 2 pi over the period or 2 pi times the frequency. So we're going to talk specifically now about some other important things with a wave. What makes it different than that periodic motion stuff we talked about? Well, it still has an amplitude. That's the displacement of the wave's medium from the midline. So the medium is whatever the wave is traveling through. Most waves are mechanical waves, and mechanical waves require a medium to travel through. We'll talk later about a particular type of wave that doesn't need a medium. So mechanical waves need a medium, and that's what the wave is displacing. So if you have an ocean wave, the medium is the ocean. If you have a wave at a stadium, the people are the medium. And if you have like an earthquake, a wave that's going through there, like a S wave or a P wave, that is the earth that is displacing there. Next, we have two words, crest and a trough. Those refer to these points here. So a crest is a point of maximum positive amplitude where the wave goes up. And then a trough would be a point of maximum negative amplitude where the wave goes down. So you have an alternating version of crest, trough, crest, trough, crest, trough here. The next one is the wavelength. Wavelength is the distance traveled in one wave cycle, or the distance between successive crests or successive troughs. It's very similar to period. Period was the time for one wave cycle, but unlike in periodic motion, where we're thinking about like a pendulum moving back and forth, we're now thinking about something that's actually traveling from one place to another. That's the big difference about waves rather than just simple harmonic motion, is that there's actually a travel over some distance. And so to help with that, we want to think about the wavelength, which is the distance between two successive points there. So one wavelength, they've given it here as well, is given the symbol lambda. So this Greek symbol lambda is our wavelength, and it's simply measured, of course, in units of length, so meters or centimeters or something like that. And then, of course, good old phase we've talked about, where phase is the offset of a wave from a particular point. We talked about phase angle, but we can also think about it in terms of degrees or radians if we wanted to as well. So those are some basic properties of looking at a wave. Now, there's a bunch of different types of waves. One way to look at a type of wave is what direction the medium is displaced in. You've got transverse waves and longitudinal wave. In a transverse wave, the wave's displacement is perpendicular to what direction the wave is traveling in. So here's a picture here. If my wave is traveling this way to the right and it's moving up and down and up and down, I can see that the wave motion is perpendicular to that displacement of that wave. An ocean wave is similar to this, where it goes up and down and up and down and up and down. So many different waves that we've seen around do this. Another good example of this one is actually light. If you've seen depictions of light waves, they're always done with this transverse type of motion. One way I remember it is if you think about perpendicular, you think about this symbol here, which looks like an upside down T. So transverse, perpendicular, T. That's how you know it's the opposite direction of that wave travel. Longitudinal waves, the wave's displacement is parallel to the direction of wave travel. So this one's a little bit trickier, and the picture is a little funky looking. So here, what's going on is if your wave is traveling from left to right here, your wave is actually waving in the same direction that it is moving. This is a much more rare type of wave. But if you think about a slinky, you can get a slinky to kind of do that motion where the wave goes back and forth in the direction the wave is traveling. There's a couple of extra terms here to know that instead of calling them crests and troughs, we call them compressions and rarefactions, where compressions are where there's a denser part of the medium and rarefactions are where there's like a less dense part of your medium there. The biggest example of a longitudinal wave, this comes up all the time, is sound. Sound, which is a wave that we can hear auditorily, is a longitudinal wave. And I love this example. If you've ever seen on a computer or any electrical device that like the universal symbol for sound, if you think about it, it's always a speaker or something like this. And then they draw out like that. That looks like a longitudinal wave. That does not look like a transverse wave. So think about that symbol for sound. They always depict it like these wave fronts like that. That's a good way to remember that it is a longitudinal wave there. So that's transverse versus longitudinal, but now I want to talk about how do we know the speed of a wave? Well, the wave speed or velocity describes the speed that a wave pulse travels past a particular point in space. Mathematically, wave speed is just frequency times wavelength. So V is my speed, F is my frequency, and lambda here is my wavelength. Now, you might take a look at different things and say, hey, how would this change a wave speed? For example, if I have a wave that I'm doing in a slinky and I make it beat faster, so a higher frequency, would that change the speed of my wave? Well, what'll happen, you'll find, is that if you increase the frequency, the wavelength will decrease to keep the speed exactly the same. There are not many things that change the speed of a wave. In fact, we're going to say that the speed depends on the medium and only the medium of the wave. And of course, the type. So a transverse wave might be faster or slower than a longitudinal wave if you have a medium that can do both of them, of course. But other than that, it's only the medium that affects the speed of a wave. Other than that, all transverse waves in water will have a particular speed. So let's do some problems with this one here. First one is, what's the velocity of a wave in a ripple tank? It has a frequency of 3 hertz and a wavelength of 2.5 centimeters. So we know V is equal to frequency times wavelength. V here is going to be my frequency, 3 hertz, times my wavelength, 2.5 centimeters there. 3 times 2.5 is 7.5 centimeters per second here. And per second, that inverse second just comes from that. That's what a hertz is. Remember, hertz is our unit of frequency, but it also means inverse seconds, which is the same as 1/seconds. Or you could have changed this to meters per second, and that would be fine as well. Number 2 here, I want to use that same equation to find the velocity of my wave, but now they've given me period, not frequency. So remember that period is 1 over the frequency. So I do 0.02 seconds equals 1 over the frequency, and frequency is 50 hertz. So now I can plug in 50 hertz times wavelength, which is 3 meters, and I get 150 meters per second. So that's quite a fast wave. Well, sorry for the noises here. Georgie, my dog, decided to join me for this video today, and he is being loud and rambunctious. George, do you want to say hi to everybody? Come on up, buddy. George. Yes, I know, buddy. Say hi to everyone. Hi. Guys, thank you so much for a good video, and I will see you guys later. Thank you so much.